7.2 Graph exponential decay functions. The half-life equation is an example of an exponential decay function that we're not actually going to talk about in this lesson here, but you'll see it all over chemistry, you'll see it again in math, and so of course I needed you to get a half-life for this lesson. So in the last lesson, we talked about functions of the form y equals ab to the x, and we said that we better say that a does not equal 0, and we've got to have b is positive, and b cannot be equal to 1. That was what we explained in the last lesson. Today, we're going to be talking about exponential decay functions. And in the last lesson, you might remember that we were concentrating on a is greater than 0 and b is greater than 1. In this lesson, b is actually going to be a number between 0 and 1, and that makes it an exponential decay function. Since b is a value between 0 and 1, it is going to be a fraction that is less than 1. So just keep that in mind for now. The decay factor is just going to be your b. Instead of in the last section where we saw a growth curve that looked like this, now we will see a decay function that is coming down. Let me erase that one. So we really do much of what we saw in the last lesson. Again, you're going to have this asymptote here at y equals 0. So the asymptote is going to be at y equals 0. The range, again, this takes in any real number, so the domain is all real numbers. And the range, well, that's only strictly greater than 0 for the y values. Again, in the decay function, the function is going to be falling. Some good points to put in might be 0 and 1. Remember, we have b to the x power, so b to the 0 power is 1. So we have the point 0, 1 right there. And b to the first power is b. Now remember, we're dealing with b between 0 and 1, therefore b must be less than 1, and that's why it's falling. Let's go ahead and graph this guy. Now, before I start plotting points, I just want to show you something. Didn't we learn that 1/3 is the same thing as 3 to the negative 1 power? Okay, so that's 1/3. We're going to raise that to the x. In other words, y equals 3 to the negative x. I bet you can see why when I have a fraction here that's less than 1, I get exponential decay. I see the light bulbs going off for some of you, not so much for others of you. Bet you're going to get used to this one way or another. Let's just plot some points, just like I was doing last time. -1, 0, 1, and 2 sound good to me. So we have 1/3 to the x power. When we do 1/3 to the negative 1 power, we just flip that over and we get 3. When we do 1/3 to the 0 power, we get 1. When we do 1/3 to the first power, we get 1/3. And 1/3 to the second power is 1/3 times 1/3, or 1/9. Square the top and the bottom, don't forget. So you can see that the numbers are going down in this case. We have decay, plot -1, 3, plot 0, 1, 1, 1/3, and 2, 1/9. Make sure that you've got this asymptote here, okay? And just sketch that in. Again, I'm going to be looking for the general shape, it going through about 3 proper points, and that the asymptote is correct. So that's what your graph should look like there. Yes, we have a transformation of our last graph. We have a vertical stretch by a factor of 2. So I'm just going to take the xy points that I found in my last example. That was -1, 3, 0, 1, 1, 1/3, and 2, 1/9. And I'm just going to apply this vertical stretch, so multiply all of the y coordinates by 2. Times 2 times 2. 1, 2, 3, 4, 5, 6. Since I really have not shifted anything up or down, I do not touch my horizontal asymptote, and I plot those points. Now B, right away, I know that this is going to be reflected, so instead of looking like this, it's going to look something like this. But let's just go ahead and plot some points. So let me just do my -1, 0, 1, and 2. So in this one, I'm actually going to begin with y equals 3/4 to the x power, and then I'll multiply it by -2 after that. So I'll apply this as my second step. So first we have 3/4 to the -1 power. Just flip it over. We get 4/3. Anything to the 0 power is just 1. 3/4 to the first power is just itself, 3/4. And 3/4 squared is going to be 9/16. Make sure you're squaring the top and the bottom. Now I'm just going to do that -2 stretch. Yikes, and I ran out of room. You know what I mean. So just multiply all the y coordinates by -2. So you'll see that my reflection is going to happen right now. -8/3, 1 becomes -2, 3/4 becomes -3/2, and 9/16 becomes -9/8. So now I look at my x's and these y's to plot. So we have -1, that's -2 2/3. I have 0, -2. I have 1, -1.5. And I have 2, -1.1. Again, my horizontal asymptote has not moved in this one. I have not shifted anything up or down at all. So my graph is just going to look something like that. Fun with transformations here. Let's just start with the parent function, xy equals 1/3 to the x power. So again, the same points that we started with in the first example would be 3, 1, 1/3, and 1/9. That's just what we got in the first example. Now I'm going to apply my transformations. First thing is a vertical stretch by a factor of 2. Times 2, times 2, times 2, times 2. The second thing is going to be to shift it 2 units to the right. Add 2 to the x. 2 plus 2 plus 2. And now, final step is to shift this thing 1 unit up. So, shift it up. We're shifting it up. We should be saying to ourselves, oh, I'm going to be changing my range because my y's are going to be different. Okay, so let's get started. Our domain has not changed. Our domain is always going to be all real numbers in these. But our range, we've shifted everything 1 unit up. So instead of being 0, we've shifted it 1 unit up. Y is greater than 1 is our range. So let's go ahead and plot that as our asymptote. Our asymptote is now at y equals 1. And then we can plot the points. 1, 7. You see that we shifted everything over 2 units to the right. 2, 3. 3, 1 and 2/3. And then 4, 1 and 2/9. So we're getting real close to the asymptote there. There we go. So to graph this, you're going to begin with the parent function, apply that first vertical stretch or shrink, then do the horizontal translation of h units right, and then vertical translation of k units up. Now the exponential decay models, instead of being 1 plus r, it's going to be 1 minus r. Of course, if you start with $5 and you're going to a 10% off sale, then you would do 5 minus 10% of 5. Factor that 5 out and you get 1 minus 0.1. And that's why you do the original amount times 1 minus r, because you need to have the original amount. Just like last time, A represents the initial amount. R is just the percent decrease. Of course, express that as a decimal. So 1 minus r is the, and this should say decay factor. And t is just the time in years. One example before we close. A new car cost $25,000. The value of the car decreases by 15% each year. In other words, 0.15. Write an exponential decay model giving the car's value y in dollars after t years. Remember, we have y equals a, 1 minus r to the t power. So we just have y equals 25,000, 1 minus 0.15 to the t, in other words, 25,000 times 0.85 to the t power. Estimate the value after 4 years. Well, we just do y after 4 years. In other words, 25,000 times 0.85. If we're doing this in our calculator, hit that key to the 4, and that should give you $13,050. Let's go to our calculator to estimate when the value of the car will be $8,000. So when will this equal 8,000? So basically, if I put this in y1 and I put this in y2, I want to know, when do they intersect? Go to your y equals. In y1, we said we're going to put 8,000. In y2, we're going to put 25,000 times 0.85 to the x power. Remember, you want to put an x all the time for your variable. Of course, we need to mess with our window a little bit. We need to go up to at least 8,000. Let's go ahead and go up to 10,000 this time, since we ran into trouble last time we didn't go up enough. And those are your y values. So what should we do for our x? Well, since we're measuring time, x cannot be less than 0, and let's just go to 15 to be safe. Let's graph that. There's y equals 8,000, and there's our exponential decay model. And this would be the number of years where we see the intersection. So second calc, let's do number 5, intersect. And again, just use your left and right arrows to get right to the point. Only use your left and right. You see, if you press it up and down, you see how it goes from curve to curve? You don't want to do that. You want to stick on the same curve using your left and right arrows. Press enter 3 times, 1, 2, and 3. So our answer is after about 7 years. After 7 years.
And that's it for this lesson.
Bye.